What you call reality may be only a single page torn from a book of unimaginable size. This is not speculation pulled from imagination. It is a conclusion that keeps surfacing, uninvited, from the most carefully tested theories in physics. Scientists did not go looking for other universes. They went looking for the rules behind atoms, behind light, behind the expansion of space. And they found that those rules, followed honestly to their conclusions, point beyond the world we can see. Consider what that means. The equations describing a single particle suggest it explores many outcomes at once. The equations describing the birth of the cosmos suggest space may still be giving rise to new regions, endlessly. The equations describing the deepest layers of matter allow for an enormous number of possible universes, each with its own settings. In each case, the mathematics does not whisper about other worlds. It produces them as a matter of course. So we are left with a genuine question, not a fantasy. Are these other universes real, existing somewhere we cannot observe? Or is their constant appearance a signal that our understanding remains incomplete? In the parts ahead, we will trace this puzzle from the behavior of the smallest particles to the structure of the entire cosmos. We will look at what the theories actually claim, what could be tested and what cannot. The aim is not belief. The aim is to understand precisely why this question refuses to go away and what hangs on its answer. The word universe was once meant to settle the matter entirely. It comes from roots meaning turned into one, a single whole containing everything that exists. By definition, there could be nothing outside it, because the word was built to include all things. For most of human history, this was not a scientific claim so much as a logical one. To speak of another universe seemed like speaking of a square circle, a contradiction hiding inside the very meaning of the words. And yet here we are, with working physicists writing papers, holding conferences, and arguing in good faith about realities that lie beyond our own. Something changed. Understanding what changed is the first step toward understanding everything that follows. The shift did not come from imagination running loose. It came from the opposite direction, from taking established theories seriously and refusing to flinch at where they led. This is worth sitting with, because it inverts the usual assumption. People often picture parallel universes as a creative leap, a fanciful addition someone bolted onto physics for entertainment. The reality is closer to a reluctant admission. In several independent areas of research, scientists found that the simplest, most honest reading of their equations described more than the world in front of them. The extra universes were not invited. They arrived as unpaid guests and proved remarkably difficult to evict. To see why this matters, it helps to understand how physical theories actually work. A good theory is a compact set of rules that reproduces what we observe and predicts what we have not yet seen. When those rules are tested and confirmed again and again, they earn a kind of authority. We begin to trust their consequences, even in situations we cannot directly check. Consider how we treat the law of gravity. No one has traveled to the far side of a distant star to confirm that objects fall there too, yet we accept that they do, because the rule that governs falling has never once failed where we could test it. We extend our trust beyond our observations because the rule has earned it. This is not blind faith. It is the disciplined extension of confirmed patterns into regions we cannot reach. The trouble with parallel universes begins exactly here. Some of our most thoroughly tested theories, when extended in this same disciplined way, predict other universes as naturally as gravity predicts a falling stone on a world we have never visited. The physicist does not get to keep the parts of the theory that are comfortable and discard the parts that are strange. If the rule works all the way down, and sometimes the rule says there is more than this. To reject the other universes while accepting everything else the theory predicts would be inconsistent, a special exception made only because the conclusion unsettles us. And inconsistency is the one thing a careful scientist cannot allow. This is why the subject deserves a serious treatment rather than a dismissive one. It would be easy to wave it away as untestable speculation, and we will examine that criticism honestly in time, because it carries real weight. But it would be just as careless to pretend the idea has no foundation. The foundation is built from the same material as the rest of physics. The question is not whether the theories suggest other universes. In several cases, they plainly do. The question is what that suggestion is actually telling us, and that is a far subtler problem than it first appears. Part of the confusion comes from the word itself, which carries too much weight for the variety of ideas now crowded under it. When most people hear parallel universe, they imagine a near copy of our world, reachable through some hidden door, where a familiar version of events plays out with small differences. That image owes more to storytelling than to science, and it captures almost none of what physicists actually mean. The realities that emerge from modern theory come in distinct types, arising from different lines of reasoning, with different degrees of strangeness and different prospects for ever being tested. Treating them as a single idea is like treating every flying thing as a bird, lumping together insects, aircraft, and falling leaves because they share the sky. The differences are not details, they are the whole substance of the matter. The first type emerges from the structure of space on the largest scales. If space extends far enough, perhaps without end, then the region we can observe is only a tiny portion of a much greater whole. Other regions lying beyond the distance light has had time to cross would be governed by the same physical laws as ours, but filled with different arrangements of matter. These are not exotic at all in their underlying rules. They are simply too far away to see, separated from us by distance rather than by any deeper barrier. In a sense, they are the least controversial of all the proposals, because they require nothing more than space being larger than the part we happen to inhabit. A second type comes from the behavior of matter at the smallest scales, where the rules of quantum theory hold. Here, the strangeness is of a different character. Rather than other regions far away in space, this proposal describes other outcomes, other branches of events, coexisting in a way that defies ordinary intuition. When a particle could do one of several things, one reading of the mathematics says it does all of them, each in its own branch of reality. These branches are not distant. In a sense, they are right here, overlapping the world we know, yet sealed off from it by the very nature of how quantum events unfold. We will spend considerable time on this idea, because it is both the strangest and the most directly tied to experiments we can perform. A third type reaches deeper still, into the possibility that the fundamental constants of nature, the basic numbers that determine how strong forces are and how heavy particles can be, might take different values in different universes. In our world, these numbers have particular settings, and life depends delicately on those settings. Change them even slightly, and atoms might never form, stars might never ignite, chemistry as we know it might never arise. If other universes exist with the dials turned to other positions, then ours would be one entry in an enormous range of possibilities, most of them barren. This proposal connects to the deepest theories of matter we have, and to a question that has troubled scientists for decades, the question of why our universe seems so suited to our existence. These are only the broad categories, and within each there are finer distinctions, competing versions, and unresolved disputes. The point for now is simply this: parallel universe is not one idea, but a family of ideas, related by a common theme and separated by deep differences in origin and meaning. As we proceed, we will keep these distinctions sharp, because blurring them is the surest way to misunderstand the entire subject. A claim that sounds outrageous in one form may be almost modest in another, and the prospects for testing one type tell us nothing about the prospects for testing the rest. There is a further reason this matters beyond mere accuracy. Each type of universe rests on a different theory, and each theory is supported by a different weight of evidence. Quantum mechanics, which gives rise to the branching realities, is among the most precisely tested theories in all of science, confirmed to extraordinary accuracy in countless experiments. The inflationary expansion of the early cosmos, which produces vast regions beyond our horizon, rests on strong but less complete evidence, with details still being worked out. The deepest theories of matter, which would allow different constants in different universes, remain partly conjectural, brilliant mathematical frameworks that have not yet been confirmed by direct observation. So when we ask whether parallel universes are real, we are really asking several separate questions, each with its own answer and its own level of confidence. Some rest on bedrock, others rest on foundations still being poured. This is the landscape we are about to explore, and it is more rugged and more interesting than the simple phrase suggests. We are not chasing a single fantasy, but following several independent trails, each beginning in solid, tested science, and leading by careful steps toward conclusions that strain the imagination. At every stage, the same discipline applies. We accept what the evidence supports. We extend trusted rules only as far as honesty allows, and we mark clearly the line where confirmed knowledge ends and reasoned speculation begins. That line will move as we go, sometimes closer, sometimes farther, and keeping track of where it lies is the most important habit we can carry forward. The deepest of these trails begins not in the vastness of space, but in its opposite, in the behavior of the smallest pieces of matter we have ever studied. For it was there, in the early years of the last century, examining particles far too small to see, that scientists first encountered something that would not fit into a single, definite reality. The world at that scale did not behave like a collection of objects with fixed properties waiting to be measured. It behaved like something else entirely, something that seemed to hold multiple possibilities at once, until the moment we looked. To understand how a serious scientist could come to believe in other universes, we must first understand what they found when they looked closely at the very small, and why it broke the comfortable picture of reality that had stood for centuries. At the start of the 20th century, physics seemed nearly finished. The motions of planets, the behavior of heat, the nature of light, the workings of electricity and magnetism all appeared to be understood, governed by elegant laws that left little room for surprise. Some respected figures suggested that the great work was essentially done, that future physicists would spend their careers measuring known quantities to ever more decimal places. Then they looked closely at the very small, at the light given off by heated objects and the behavior of particles within atoms, and the comfortable picture did not merely develop cracks. It came apart entirely, and what replaced it was so strange that the scientists who built the new theory spent the rest of their lives arguing about what it meant. The first sign of trouble came from a simple observation about energy. According to the established physics of the time, energy should flow smoothly and continuously, like water from a tap, able to take any value at all. But when scientists examined the radiation emitted by hot objects, the smooth picture failed. The numbers only made sense if energy came in discrete packets, in fixed minimum amounts that could not be subdivided. It was as though water could only ever be poured in whole cups, never half a cup or a third, with nothing in between permitted. This was the first appearance of the quantum, the indivisible unit, and it suggested that nature at its foundations was grainy rather than smooth, built from countable steps rather than continuous flow. That alone would have been strange enough, but worse was coming. Scientists studying light found that it sometimes behaved like a wave, spreading and overlapping and combining in the way ripples do on the surface of a pond, and at other times behaved like a stream of separate particles, arriving in distinct individual hits. These two pictures seemed incompatible. A wave is spread out, continuous, occupying a region of space. A particle is concentrated, located at a point. Nothing in ordinary experience is both at once. A sound is a wave, a pebble is a particle, and we never confuse the two. Yet light insisted on being described as both, depending on how it was examined, and refused to settle into one identity or the other. Then came the discovery that pushed the strangeness to its limit. Matter itself, the solid stuff of particles, the tiny grains that make up atoms, also displayed this double nature. An electron, which everyone had pictured as a minute particle, a kind of vanishingly small marble, turned out to behave like a wave under the right conditions, spreading out and overlapping with itself. The hard little objects that built the world were not so hard or so little after all. They were something for which everyday language had no proper word, something that carried aspects of both wave and particle while being fully neither. The very vocabulary we use to describe reality, a vocabulary built from a lifetime of handling ordinary objects, simply did not apply at this scale. To make sense of this behavior, physicists developed a new mathematics, and at its heart sat a single object that would become the source of all the trouble to come. This object is often called the wave function, and it describes the state of a particle in a way utterly unlike the descriptions of older physics. In the older view, to describe a particle you stated its position and its motion, where it was and where it was going, two definite facts about a definite object. The wave function does something different and far stranger. It does not assign the particle a single position. Instead, it spreads across all the positions the particle might have, assigning to each a certain weight, a measure of how strongly that possibility figures into the whole. The particle, in this description, is not at one place with the others ruled out. It is described by a quantity that embraces many places at once. It is tempting to read this as mere ignorance, as a statement about what we do not yet know. We might assume the particle really is at one definite location, and the wave function simply reflects our incomplete information about which location that is, the way a weather forecast assigns probabilities to outcomes that are themselves already fixed by the underlying physics. This natural assumption turns out to be wrong, and the way we know it is wrong is one of the most important results in all of science. The particle does not have a single hidden position that the wave function fails to reveal. The spreading is not a description of our ignorance. It is a description of the particle itself, of a physical situation in which the different possibilities are all genuinely present and capable of influencing one another. We will see the proof of this shortly, and it is decisive. The behavior that reveals this most clearly is called interference, and it is the same behavior that betrays the wave-like nature of anything. When two sets of ripples meet on water, they combine. Where two crests align, they reinforce, producing a larger crest. Where a crest meets a trough, they cancel, leaving the surface flat. The result is a pattern of reinforcement and cancellation, a characteristic signature that only waves produce, because only waves have crests and troughs that can add and subtract in this way. Particles in the old picture cannot do this. Two thrown pebbles do not cancel each other into stillness. Interference is the unmistakable fingerprint of wave-like behavior, and wherever it appears, something is spreading out and overlapping with itself. The wave function interferes. This is the crucial fact. The different possibilities it describes, the different positions a particle might occupy, are not separate alternatives sitting passively side by side. They combine and interfere with one another exactly as ripples do, reinforcing in some places and canceling in others. And this interference has measurable consequences. It changes where particles end up. If the possibilities were merely a list of options, with the particle secretly occupying just one of them, there would be nothing to interfere, no crests and troughs to add and cancel. The fact that interference occurs proves that the possibilities are all physically present, all participating, all contributing to the outcome. This is the heart of the matter, and it is why the wave function cannot be dismissed as a mere accounting of our ignorance. Consider what this implies about a single particle. The wave function for one electron can spread across a region, and the parts of it in different places can interfere with each other, canceling here and reinforcing there. But interference requires at least two things to combine. If the electron is a single object at a single point, what is interfering with what? The answer the mathematics gives is that the electron, in some real sense, explores multiple paths at once, and these multiple explorations interfere. A single particle alone behaves as though it is doing several things simultaneously, and the several things it does affect one another. This is not a figure of speech or a loose way of talking. It is the most direct reading of equations that have been tested to a precision matched by almost nothing else in human knowledge. The accuracy of these equations is worth emphasizing, because it is what forces us to take their strangeness seriously. Quantum theory is not a tentative sketch or a rough approximation. Its predictions have been confirmed in experiment after experiment, sometimes to an accuracy of many decimal places, an agreement between calculation and measurement so precise that it would be like predicting the distance across a continent and being correct to within the width of a single hair. No theory in the history of science has been tested more thoroughly or passed more convincingly. Whatever discomfort its strangeness causes, We cannot set it aside as a mistake or a misunderstanding. The theory works. It works better than almost anything we have ever devised. And it tells us that the smallest pieces of reality do not have definite properties in the way we always assumed. This creates a deep puzzle, the puzzle that drives everything to come. The world we actually experience is not spread out and uncertain. When we look at an object, it is somewhere, not smeared across many places. When we measure a particle, we find it at one location, with one definite outcome, not a blend of possibilities. The chair is by the window, or it is not. Our experience is sharp, singular, definite. Yet the theory that describes the underlying reality with unmatched accuracy says that beneath this definiteness lies a spreading, interfering multiplicity, a particle exploring many paths, a wave function embracing many outcomes at once. How does the sharp, single world we live in emerge from the blurred, multiple world the mathematics describes? Where do all the other possibilities go at the moment we look? This is the central question, and it is genuinely unresolved. Different physicists give different answers, and these answers are not minor variations on a theme. They are radically different pictures of what reality fundamentally is. Some say the act of measurement somehow collapses the many possibilities down to one, though no one can say precisely what measurement is or how the collapse occurs. Others say the possibilities never collapse at all, that they all continue to exist, and that the single outcome we experience is merely the one our particular branch of reality follows. This second answer, taken seriously and followed to its conclusion, leads directly to the idea that every quantum event divides reality, that all the possibilities the wave function describes are equally real, each unfolding in its own version of the world. To see how a respected physicist could arrive at such a conclusion, and why it may be the most natural reading of all, we need to look closely at the single experiment that displays the puzzle in its purest and most undeniable form. The experiment is simple enough to describe in a sentence, and its results have unsettled physicists for the better part of a century. Take a barrier with two narrow openings cut into it, side by side. Send particles toward it, one at a time, and record where each one lands on a screen positioned behind the barrier. That is the entire setup. There is nothing elaborate about it, no exotic equipment beyond what a competent laboratory can assemble, and yet the outcome forces a choice between possibilities so strange that no one has ever found a comfortable way to accept any of them. This is the experiment that lies at the foundation of the whole question of other realities, and it rewards slow, careful attention. Begin with what we would expect from ordinary objects, because the contrast is everything. Imagine firing small pellets at a barrier with two gaps. Each pellet passes through one gap or the other and strikes the screen behind. After firing many pellets, we would find two bands of impacts on the screen, one band lined up behind each gap, where the pellets that happened to pass through that opening accumulated. This is exactly what common sense predicts. Each pellet goes through one opening. The openings are separate, and so the marks gather in two distinct groups. Nothing about this is surprising. It is how thrown objects behave, and we could repeat it with marbles or grains of sand or any small solid thing and get the same two bands every time. Now consider what waves do in the same situation, because here the result is different and equally familiar from everyday life. Picture water waves approaching a barrier with two gaps. As each wave reaches the barrier, the two gaps each become a new source of ripples spreading outward on the far side. These two sets of ripples then overlap, and where they overlap, they interfere. Where two crests meet, they combine into a higher crest. Where a crest meets a trough, they cancel into stillness. The result on the far side is not two bands, but a series of them, alternating regions of strong wave motion and regions of calm, spread across the whole surface. This striped pattern of reinforcement and cancellation is the interference pattern, and it is the unmistakable mark of waves passing through two openings at once and combining beyond them. So we have two clear predictions, depending on what we send through. Particles, going through one gap or the other, produce two bands. Waves, passing through both gaps and interfering, produce many bands in a striped pattern. These outcomes are visibly different. Anyone could tell them apart at a glance, and this difference gives us a clean test of what any given thing actually is. Send it through the two openings, look at the screen, and the pattern reveals its nature. Two bands mean particles. Many bands mean waves. The experiment becomes a kind of question we can put directly to nature, and nature answers in a way no one can mistake. Now send electrons. Electrons are particles, or so everyone long believed, the small constituents of atoms, tiny grains of matter that we picture as minute objects with definite locations. We fire them at the barrier, one after another, and each electron strikes the screen and leaves a single small mark at a single definite point. This is exactly what particles should do. Each arrival is a distinct dot, a localized impact, with no spreading or smearing. Watching the marks appear one by one, we see nothing wave-like at all. Each electron behaves like a tiny pellet, landing at a particular spot, leaving a particular dot. So far, the picture of electrons as small particles holds up perfectly, and we might expect that as the dots accumulate, they will form two bands, one behind each opening, just as the pellets did. They do not. As the electrons continue to arrive, dot by dot, each one landing at a single definite point, the dots gradually build up a pattern on the screen. And the pattern is not two bands. It is many bands, the striped pattern of alternating dense and sparse regions, the unmistakable signature of wave interference. The individual electrons arrive as particles, one dot at a time, yet collectively they assemble the pattern that only waves produce. This is the result that breaks everything. Each electron is a particle when it lands, but the population of electrons behaves as though each one were a wave passing through both openings and interfering with itself on the way to the screen. Pause on how strange this is. The interference pattern requires something to pass through both openings and combine on the far side. With water waves, this is straightforward, because a water wave is a spread-out thing that naturally covers both gaps at once. But the electrons are sent one at a time. At any given moment, there is only a single electron in the apparatus, traveling alone from the source toward the screen. There is no second electron for it to interfere with. The pattern cannot come from different electrons combining, because they pass through one by one, often with long gaps between them, each completing its journey before the next begins. Whatever produces the interference must be happening to each electron individually, on its own, in isolation. The conclusion is difficult to avoid and harder to accept. Each single electron, traveling alone, must somehow pass through both openings at once and interfere with itself. There is no other way to produce the pattern. The electron does not go through one gap or the other, the way a pellet would. It goes through both as a wave would, and the two parts of its passage combine on the far side to steer where it can and cannot land. The interference pattern is built up from many electrons, but the interference itself happens within each one. A single, indivisible particle behaves as though it explores two separate routes simultaneously, and the two routes interfere with each other before the electron commits to a single point of arrival. Surely, one thinks, this can be checked. If each electron really passes through both openings, we could place a detector at the openings and watch it happen. We could see the electron split, or catch it going through both, or at the very least confirm directly that it does not simply choose one gap like an ordinary particle. So physicists do exactly this. They place detectors at the openings to observe which one each electron passes through. And here, the experiment delivers its final and most disorienting result. When we watch the openings, we always catch each electron passing through one opening only, never both. It goes through the left or it goes through the right, like a proper particle, never splitting, never appearing in two places. The act of watching shows us a single electron taking a single, definite path. But when we watch the openings in this way, the interference pattern vanishes. The moment we observe which opening each electron uses, the striped pattern on the screen disappears and is replaced by two simple bands, exactly what ordinary particles would produce. By looking, we have changed the outcome. The electrons that we watch behave like particles going through one gap, producing two bands. The electrons we do not watch behave like waves going through both gaps, producing many bands. The mere act of acquiring information about the path destroys the interference. Stop watching, and the interference returns. The pattern depends not just on what the electrons do, but on what we choose to find out about them. This is the experiment in its complete form, and every part of it has been confirmed countless times with great care. It is not a puzzle awaiting a clever resolution that everyone has somehow overlooked. The strangeness is real, and it is permanent. When unobserved, each particle behaves as though it travels multiple paths and interferes with itself. When observed, each particle is found on a single, definite path, and the interference disappears. The behavior of the smallest pieces of matter depends on whether their paths are known. This is not a statement about clumsy measurement disturbing a delicate system, though that explanation is sometimes offered. The dependence on observation runs deeper than any physical jostling, and reaches into the question of what counts as a definite fact about the world at all. We are now in a position to state the puzzle with full precision. The wave function describes each electron as exploring both paths, and the interference pattern confirms that this exploration is physically real, because only genuinely present and combining possibilities can interfere. Yet, whenever we look, we find a single electron on a single path, and the multiplicity vanishes along with the interference. So which is true? Does the electron really travel both paths, as the unobserved interference insists? Or does it travel one path, as every observation reveals? The mathematics says both possibilities are present and combining. Our every measurement says only one possibility is ever found. Reconciling these two facts is the problem that has divided physicists for generations, and the way one chooses to reconcile them determines everything that follows. One particular way of resolving it, the most direct and least evasive way, leads straight to the conclusion that the other path is not erased when we look, but continues onward in a version of reality we simply do not inhabit. It is to that resolution, and the bold thinker who proposed it, that we now turn. For decades, the standard response to this puzzle was to declare that observation causes the multiple possibilities to collapse into one. Before measurement, the electron explores both paths, described by a spreading wave function. At the moment of measurement, the wave function collapses. All possibilities but one vanish instantly, and the electron snaps into a single, definite state. This idea, worked out by the founders of quantum theory, allowed physicists to calculate results with perfect accuracy, and for practical purposes, it was enough. You applied the rules, the wave function collapsed when you measured, and the numbers came out right. Generations of physicists were taught to use this recipe, and not to ask too many questions about what it meant. The approach even acquired a famous piece of advice, often paraphrased as a suggestion to stop worrying and simply calculate. But the collapse, examined closely, raises questions it cannot answer. What exactly counts as a measurement? The wave function is supposed to evolve smoothly, predictably, according to a precise equation, right up until a measurement occurs, at which point it abruptly collapses according to entirely different rules. So where is the line? What physical process draws the boundary between the smooth evolution and the sudden collapse? A measuring device is itself made of particles, atoms, electrons, all governed by the same quantum rules as the electron being measured. If everything is made of quantum pieces, and quantum pieces evolve smoothly, then what introduces the sudden break? At what point, and by what mechanism, does the lawful spreading give way to the lawless snap? The theory that predicts experimental results to staggering precision falls silent precisely here, at the question of what a measurement actually is. This silence troubled a graduate student named Hugh Everett in the 1950s, and his response was as simple as it was radical. He asked what would happen if we took the equation seriously and never allowed the collapse at all. The wave function evolves smoothly, always, with no exceptions, no special rules for measurement, no sudden snapping into a single state. The same equation that governs the electron between measurements governs it during measurement too, and governs the measuring device, and governs the physicist reading the device, and governs everything without interruption forever. It was the most conservative possible move, in a sense, because it removed the awkward extra rule rather than adding anything. And yet its consequences are the most expansive in all of physics. Follow the reasoning carefully, because it is the crux of the entire idea. An electron approaches the two openings, described by a wave function that explores both paths. A detector waits to record which path it takes. In the old picture, the detector measures the electron, the wave function collapses, and the electron is found on one path. But Everett forbids the collapse. So what happens instead? The detector is made of particles, and those particles interact with the electron, according to the same smooth equation. The part of the wave function in which the electron went left causes the detector to register left. The part in which the electron went right causes the detector to register right. Both parts evolve smoothly and simultaneously. The detector does not collapse the electron into one path. Instead, the detector itself enters a combined state, a state in which it has registered left and registered right at the same time. Now extend this one step further. the step that changes everything. A physicist looks at the detector to read the result. The physicist, too, is made of particles governed by the same equation. The part of the wave function in which the detector reads left causes the physicist to see left. The part in which the detector reads right causes the physicist to see right. Both parts continue to evolve smoothly. So the physicist enters a combined state as well, a state containing a version who saw left and a version who saw right, both fully real, both present in the wave function, neither one collapsing the other away. The multiplicity has not been resolved by observation. It has spread outward from the electron to the detector to the observer, swallowing each in turn, until the observer themselves exists in multiple versions, each having seen a different outcome. This is the heart of what came to be called the many worlds interpretation. There is no collapse. There is only the wave function, evolving smoothly and eternally. And as it evolves, it continually divides into branches. In one branch, the electron went left, the detector read left, the physicist saw left, and everything in that branch is consistent with that outcome. In another branch, everything is consistent with the opposite outcome. The two branches are equally real, both contained in the single wave function, both governed by the same unbroken equation. The single definite outcome each version of the physicist experiences is not the only outcome. It is merely the outcome in their particular branch. The other outcomes did not vanish. They are proceeding just as fully in branches the physicist can no longer reach. It is worth being precise about what is splitting and what is not. The world does not duplicate by some mysterious creation of new matter or new space. Nothing is added. The wave function was always capable of describing multiple outcomes at once, as the interference experiment proved. What changes during a measurement is that these multiple outcomes, which were previously able to interfere and recombine, become separated in a way that prevents them from ever influencing one another again. The branches stop overlapping. Each one carries on as a complete, self-consistent version of events, containing its own version of every object and every observer involved, none of them aware of the others. The splitting is not a multiplication of stuff. It is a division of the single existing wave function into parts that can no longer communicate. The appeal of this idea to those who find it appealing is its economy. It adds nothing to the equation. It removes the troublesome collapse, the rule no one could define, the boundary no one could locate. It takes the mathematics that work so superbly and simply declines to interrupt it with a special exception. In return for this restraint, it asks us to accept that reality is vastly larger than we thought, constantly dividing into branches, each containing its own version of us. The strangeness is moved out of the equations, which become clean and unbroken, and into the picture of reality the equations describe, which becomes almost unimaginably vast. To its supporters, this is a fair trade, even an elegant one. The theory becomes simpler at the cost of the world becoming larger. To its critics, the trade is no bargain at all. They point out that we are being asked to believe in an enormous, ever-growing collection of unobservable worlds, none of which we can ever detect, all to avoid the inconvenience of a collapse we could simply accept. Multiplying entire universes to simplify an equation strikes them as the opposite of economy. There is also the deep question of what probability means in such a picture. In ordinary quantum theory, The wave function tells us the probability of each outcome, and some outcomes are more likely than others. But if every outcome actually happens in some branch, then what does it mean to say one is more probable than another? When every possibility is realized, the notion of probability seems to lose its footing, and yet probability is essential to how quantum theory connects to experiment. This problem is subtle and remains genuinely contested, with proposed solutions that some find convincing and others do not. These objections are serious, and the many worlds interpretation is not the consensus view among physicists, though it commands real and growing support. It is one of several competing interpretations, each with its own strengths and difficulties, and the disagreement among them is not a sign of confusion, so much as a sign of how deep the underlying puzzle runs. What all the interpretations share is the same mathematics, the same predictions, the same flawless agreement with experiment. They differ only in the story they tell about what the mathematics means, about what is actually happening beneath the numbers, and this is precisely why the question is so hard to settle. The interpretations agree on everything we can measure and disagree on everything we cannot. Notice the peculiar nature of this disagreement. Every interpretation predicts exactly the same experimental results because they all use the same equation to calculate. Whether the wave function collapses or branches, the probabilities of what we will observe come out identical. This means no experiment yet devised can distinguish between them. They are not different theories making different predictions, which we could test against each other. They are different pictures attached to a single theory, all consistent with everything we have ever seen. Choosing among them has so far been a matter of judgment, of which assumptions one is willing to make, rather than a matter of evidence settling the question. Some physicists find this an acceptable situation. Others find it intolerable, a sign that we have not yet found the right way to think about quantum reality at all. But the many worlds picture leaves us with a pressing question of its own, one that any honest version of the idea must confront directly. If reality is truly branching constantly, dividing with every quantum event into countless versions, then why do we never notice? Why does our experience feel so seamless, so singular, so utterly devoid of any sense of splitting? We do not feel ourselves dividing. We do not glimpse the other branches or sense the moment of separation. Each of us experiences one smooth, continuous, unbroken life, with no hint of the vast multiplicity the theory describes. If we are constantly splitting into copies, the absence of any sensation of it demands an explanation. There must be a reason the branches separate so cleanly, so completely, that no trace of one ever leaks into another. That reason has a name, and understanding it is the key to making the entire picture coherent. The answer lies in a process called decoherence, and it is one of the genuine achievements of modern physics, a piece of solid, calculable science that brings rigor to what might otherwise remain pure speculation. Decoherence explains why the branches of the wave function separate so cleanly that they can never again influence one another, why we never sense ourselves dividing, and why the world of our experience looks so sharply defined, despite resting on a blurred and multiple foundation. Unlike the interpretations themselves, which remain contested, decoherence is not a matter of opinion. It is a physical process that can be described mathematically, observed in the laboratory, and measured with precision. Understanding it is what separates the many worlds idea from idle fantasy, and roots it in testable physics. Return to the interference experiment because it holds the key. Recall that a single electron, when unobserved, passes through both openings and interferes with itself, producing the striped pattern. The interference is possible because the two parts of the electron's journey, the part going left and the part going right, remain able to combine. They are coherent, which means they maintain a definite relationship that allows them to add and cancel like the crests and troughs of overlapping waves. This coherence is delicate. It is what makes the multiple possibilities able to interfere, and therefore what keeps them bound together as parts of a single, undivided quantum situation. As long as coherence is preserved, the possibilities have not separated into distinct branches. They are still one interfering whole. Now recall what destroyed the interference. The moment we placed detectors at the openings to record which path the electron took, the striped pattern vanished and was replaced by two simple bands. The act of recording the path destroyed the coherence between the two possibilities. Once the detector registered which way the electron went, the left-going part and the right-going part could no longer combine, and the interference disappeared. This loss of coherence is decoherence, and the crucial insight of modern physics is understanding exactly why it happens and what it requires. It is not the watching itself in any mystical sense that matters. It is the physical recording of information about the path, the unavoidable interaction between the electron and something else that comes to carry a trace of where it went. Here is the essential point. For two possibilities to interfere, they must be kept perfectly isolated from the rest of the world. The slightest interaction that records which possibility occurred, anywhere, in any physical system, destroys the coherence and prevents the interference. When a detector registers the electron's path, the detector now carries information about that path, and this is enough to break the coherence, whether or not any human ever reads the detector. The information has leaked out of the isolated electron into the wider world, and once it has leaked, the possibilities can no longer recombine. They have become, in the precise technical sense, separate branches. Decoherence is the leaking of information into the surrounding environment, and it is what converts overlapping, interfering possibilities into distinct, isolated branches that can never again meet. This transforms our understanding of when and why branching occurs. A single electron in perfect isolation does not branch. Its possibilities interfere, remaining coherent, remaining one undivided whole. But nothing in the everyday world is ever in perfect isolation. Every object is constantly bombarded by particles of light, jostled by air molecules, bathed in radiation, touched at every instant by the countless particles that fill its surroundings. Each of these interactions carries away a little information about the object's state. And the larger the object, the more such interactions it undergoes, the faster the information leaks, and the faster coherence is destroyed. For anything bigger than the smallest particles, decoherence is essentially instantaneous, far too fast to notice, far too thorough to reverse. This is why we never see large objects in the blurred, interfering states that small particles display. A single electron, well isolated, can be kept in a state exploring multiple paths, and its interference can be measured. But a baseball, or a chair, or a person is composed of an enormous number of particles, each in constant interaction with its surroundings. The information about the state of such an object leaks into the environment almost instantly, through countless tiny interactions, so the different possibilities decohere immediately and become separate branches before any interference could possibly occur. The reason a chair is never seen in two places at once is not that quantum theory fails to apply to chairs. It is that the chair decoheres so rapidly that its branches separate faster than any observation could ever catch them overlapping. Decoherence also explains a feature of the experiment that might otherwise seem arbitrary, namely, which properties become definite. When the environment records information about a particle, it does not record everything equally. It tends to record position, where things are, because that is what most physical interactions naturally register. A particle of light bouncing off an object carries away information about where the object was. As a result, position becomes the property that decoheres fastest, the property that becomes sharp and definite in our experience, while other, less robust properties remain blurred. This is why the world we see is a world of objects in definite places. The environment, through countless interactions, is constantly measuring position, constantly forcing it to become definite, constantly converting positional possibilities into separate branches. The sharp, located world of experience is the world that decoherence carves out of the underlying blur. Now we can answer the question of why we never feel ourselves splitting. A human being is among the most thoroughly interacting objects imaginable, composed of an immense number of particles, constantly exchanging information with the environment through light, heat, sound, and touch. The moment any quantum event affects us, even slightly, the information about its outcome floods into our surroundings and into the particles that compose us, and decoherence separates the outcomes into distinct branches faster than thought, faster than perception, faster than any process in the brain could register. By the time we become aware of an outcome, the branching is long complete, thorough, and irreversible. There is no moment of division to perceive because the division happens far below and far before the threshold of awareness. Each version of us finds itself in a single branch, with a single definite history, no more able to sense the others than the electron's two paths can recombine once recorded. This is the feature that makes the branches truly separate, rather than merely hidden. Once decoherence has occurred, the branches cannot influence one another, not even in principle. The interference that bound them together is gone, destroyed by the leaking of information, and it cannot be restored, because the information has spread into countless particles across an ever-widening region and could never be gathered back. The branches are not parallel in the sense of running alongside each other within reach. They are sealed off completely, each evolving according to its own consistent history, none able to send so much as a single bit of information to another. This is why, if the many worlds picture is correct, we can never observe the other branches. Decoherence does not merely hide them, it severs them cleanly and permanently. There is something almost satisfying in how decoherence converts a philosophical puzzle into a physical process. The old question of what counts as a measurement, the question that the collapse idea could never answer, dissolves. A measurement is simply any interaction that records information about a system into its environment thoroughly enough that the resulting branches decohere. There is no need for a conscious observer, no need for a mysterious boundary between the quantum and the everyday. There is only the leaking of information, happening continuously, everywhere, at rates that depend on how strongly a system interacts with its surroundings. The transition from the blurred quantum world to the sharp classical world is not a sudden magical collapse, but a smooth, calculable, well-understood process of information spreading into the environment. This is genuine physics, confirmed in laboratories where the rate of decoherence can be measured and even slowed by carefully isolating systems from their surroundings. It is important to be clear about what decoherence does and does not settle. It explains rigorously why the branches separate, why we never see interference in large objects, and why our experience is sharp and singular. These are real accomplishments, not interpretations, but established physics. What decoherence does not do by itself is tell us whether the other branches are real. It explains why, if they exist, we cannot perceive them. But whether they truly exist, or whether only one of them is somehow selected to be real while the others are mere mathematical ghosts, is the question that still divides the interpretations. Decoherence is common ground. Everyone accepts it. The disagreement is about what to make of the branches it produces, whether to regard them as fully real parallel histories or as a calculational device that describes outcomes that do not all come to pass. What decoherence has given us, regardless of which interpretation one favors, is a precise and physical account of how multiplicity at the quantum scale becomes the definite, singular world we inhabit. And it has shown that this multiplicity, real or not, is a natural and unavoidable consequence of taking quantum theory seriously and applying it consistently to everything, including the measuring devices and the observers. The smallest scales of reality, then, offer one route to the idea of parallel realities, a route paved with the most precisely tested physics we possess. But it is not the only route, and it may not even be the most direct. For while we have been looking inward at the behavior of the very small, an entirely separate line of reasoning has been pointing outward, toward the largest scales of all, toward the origin and structure of space itself. There, in the story of how the cosmos began and how vast it may truly be, other universes appear again, arising not from the strangeness of particles, but from the sheer immensity of space and the violent expansion that brought it into being. Look up on a clear night, and the universe seems finite, bounded by the darkness between the stars. But the darkness is misleading. The cosmos extends vastly beyond what any eye or telescope can detect, and the story of how it reached its present size points towards something that the early scientists who first studied it never anticipated. The universe did not expand gently or gradually in its first moments. According to the leading account of cosmic origins, it underwent a burst of expansion so rapid and so enormous that the numbers describing it strain comprehension. And this burst, examined closely, suggests that our universe may be one of an immense and possibly endless multitude. The idea is called inflation, and it began as a solution to entirely different problems before its deeper implications became clear. To understand inflation, we must first understand the puzzles it was invented to solve, because those puzzles are what give it credibility. When scientists examined the universe on the largest scales, they found two features that ordinary expansion could not explain. The first was its remarkable uniformity. Look in one direction at the faint glow left over from the early universe, and you find a particular temperature. Look in the opposite direction at a region so far away that it lies on the other side of the observable cosmos, and you find almost exactly the same temperature, matched to extraordinary precision. This is strange, because these two regions are so far apart that light, the fastest thing there is, could never have traveled between them in the entire history of the universe. They have never been in contact. Nothing could have passed from one to the other. So how did they come to have the same temperature? Regions that have never interacted should not match so precisely. It would be like finding two distant islands whose inhabitants had never met, speaking an identical language down to the smallest detail. The second puzzle concerned the geometry of space itself. Space can in principle be curved, bent by the matter and energy within it, like the curved surface of a sphere or the flaring surface of a saddle. Yet measurements show that space, on the largest scales, is remarkably flat, straight, and true to a high degree of precision. This flatness is puzzling because it is unstable. Any small curvature in the early universe should have grown enormously as the universe expanded, magnified over billions of years into something easily detectable. For space to appear so flat now, it must have been almost perfectly flat at the beginning, balanced on a knife edge with impossible precision. Ordinary expansion offered no reason for such a finely balanced starting point. It simply had to be assumed, an unexplained coincidence built into the initial conditions. Inflation solves both puzzles at once, and the elegance of this double solution is what won it widespread acceptance. The idea is that in the first tiny fraction of a second, before the ordinary expansion took over, the universe expanded at a stupendous rate, doubling in size again and again in an almost inconceivably short time, growing by an enormous factor before the burst ended. This rapid expansion explains the uniformity, because the entire observable universe grew from a region small enough to have been in contact before inflation began. That tiny region reached a common temperature while it was still small and connected, and then inflation stretched it to enormous size, carrying the uniformity along with it. The matching temperatures in opposite directions are simply different parts of what was once a single, small, well-mixed region, blown up to cosmic scale. Inflation explains the flatness just as naturally. Take any curved surface and magnify a small piece of it enormously, and that piece appears flat, in the same way that the surface of the Earth appears flat to someone standing on it, because we see only a tiny magnified portion of a vast sphere. Inflation stretched space by such a colossal factor that whatever curvature it began with was flattened out, smoothed to near perfect straightness by the sheer scale of the expansion. The flatness we observe is not a finely balanced coincidence, but the inevitable result of stretching space so violently that any initial curvature became undetectable. Two long-standing puzzles, the uniformity and the flatness, both dissolve under the single idea of a brief, enormous early expansion. The success of inflation in explaining these features, along with others we have not detailed, gave physicists strong reason to take it seriously. It made predictions about the precise pattern of tiny temperature variations in the early universe, the slight ripples that would later grow into galaxies, and those predictions were confirmed by detailed measurements of the cosmic glow. Inflation is not idle speculation. It is a theory with genuine evidence behind it, accepted by most cosmologists as the best account of the universe's earliest moments. And it is precisely because inflation rests on this evidence that its further implications cannot be lightly dismissed. For when physicists examined the inflationary process more closely, asking how it begins and how it ends, they discovered something they had not set out to find. The discovery concerns how inflation stops. Inflation is driven by a particular kind of energy filling space, an energy that causes the violent expansion. For our universe to exist as it does, this expansion had to end. The inflationary energy had to convert into ordinary matter and radiation, and the calmer expansion we observe today had to take over. This ending is called reheating, the moment the inflationary energy transforms into the particles that would eventually become stars and galaxies and everything else. The puzzle is that the ending does not happen everywhere at once. Inflation is a quantum process, and like all quantum processes, it is subject to the spreading and uncertainty we have already encountered. The inflationary energy does not convert uniformly across all of space at a single instant. It converts here and there, in some regions before others, governed by quantum chance. This unevenness has a profound consequence. While inflation ends in some regions, producing pockets of ordinary space like the one we inhabit, the space between these pockets continues to inflate. And because inflation expands space so rapidly, the inflating regions grow far faster than the pockets where it has ended. New space is created by inflation more quickly than inflation switches off within it. The result is that inflation, once started, may never fully stop. It ends locally in scattered pockets, but globally it continues forever, perpetually generating new inflating space, within which new pockets of ordinary space continually form. This is called eternal inflation, and it emerges not as an added assumption, but as a natural consequence of combining inflation with the quantum uncertainty that governs how it ends. Consider what this picture describes. There is a vast, perhaps endless expanse of inflating space, expanding at a furious rate. Scattered throughout it, like bubbles forming in a boiling liquid, are pockets where inflation has ended and ordinary universes have formed. Each pocket is a region where the inflationary energy converted into matter and radiation, where stars and galaxies could develop, where a universe much like ours might exist. Our entire observable universe, everything we can see, every galaxy our telescopes detect, would be the contents of a single such pocket. And beyond it, separated by regions of still inflating space, would be countless other pockets, other universes, each one formed by the same process, each one a bubble of ordinary space within the endlessly inflating whole. The expansion that began our universe did not happen once. It happens perpetually, budding off new universes without end. These pocket universes are separated from one another in a way that makes them effectively unreachable, and the reason is the same furious expansion that creates them. Between any two pockets lies inflating space, and that space expands so rapidly that the distance between the pockets grows faster than anything could ever cross it. Even light, traveling at the ultimate speed, could never traverse the swelling gulf of inflating space that separates one pocket from another, because that gulf stretches faster than light can advance across it. The pockets are carried apart more quickly than any signal could ever bridge them. Each is an isolated island universe, formed from the same inflationary ocean, yet sealed off from all the others by the relentless expansion of the space between. They share a common origin, but can never share anything else. This is a different route to parallel universes than the branching of quantum theory, and it is worth marking the contrast clearly. The quantum branches arise from the multiplicity of outcomes at the smallest scales, separated by decoherence, overlapping our own world, yet sealed off by the loss of coherence. The inflationary pockets arise from the multiplicity of regions at the largest scales, separated by inflating space, distant from our own world, and sealed off by expansion. One comes from the strangeness of the very small, the other from the immensity of the very large. They are independent ideas, emerging from independent theories, each supported by its own evidence and reasoning. That two such different lines of thought both point toward other universes is, to some physicists, a striking pattern worth noticing, even if neither alone is conclusive. The inflationary picture also opens a possibility that the quantum branches do not, and it is this possibility that makes eternal inflation so consequential. If the different pockets formed under slightly different conditions, they might not all be alike. The process that ends inflation and sets the properties of each pocket is subject to quantum chance, and this chance might produce pockets with different characteristics, perhaps even different physical laws or different values for the basic constants of nature. Our pocket would then be one of an enormous variety, each with its own settings, most of them quite unlike ours. This connects the cosmic story to the quantum story in an unexpected way, and it raises the question of just how varied these pockets might be, and whether any of them, including the part of our own that lies beyond our sight, might contain something or someone remarkably familiar. But before we can explore that, we need to confront a basic limit on what we can ever know about the universe, a limit imposed by the finite speed of light and the finite age of the cosmos, a horizon beyond which everything is hidden from us forever. Every observation we make of the universe is an observation of the past. When you look at the sun, you see it as it was several minutes ago, because that is how long its light takes to reach you. When you look at a distant galaxy, you see it as it was millions or billions of years ago, when the light now entering your telescope first set out on its journey. This is not a limitation of our instruments. It is a fundamental feature of how information travels through the universe, and it imposes a hard boundary on how much of the cosmos we can ever observe. That boundary is called the cosmic horizon, and understanding it is essential to understanding why other universes, even ones governed by exactly the same laws as ours, might lie permanently beyond our reach. The horizon arises from two simple facts combined. The first is that light travels at a finite speed. Fast as it is, light does not arrive instantly. It takes time to cross any distance, and the greater the distance, the longer it takes. The second fact is that the universe has a finite age. It began at a definite moment in the past, and only a certain amount of time has elapsed since then. Put these two facts together, and a limit immediately follows. Light can only have traveled a certain maximum distance since the universe began, because it has only had a finite time to travel and moves at a finite speed. Any object farther away than this maximum distance has light that has not yet had time to reach us. We cannot see it, not because it is too faint, but because its light is still on the way and will not arrive for ages yet, if ever. This defines the observable universe, the sphere of space around us from which light has had time to arrive. Everything within this sphere is potentially visible, its light having completed the journey to our telescopes. Everything beyond it is invisible, its light still in transit or never to arrive at all. The edge of this sphere is the cosmic horizon. It is not a physical barrier, not a wall or an edge to space itself. Space continues beyond it, presumably filled with galaxies much like those we see. The horizon is simply the limit of what light has had time to show us, a boundary set by the speed of light and the age of the universe, beyond which the cosmos is hidden not by distance alone, but by time, by the fact that not enough of it has passed for the light to complete its crossing. It is natural to assume that the universe ends, or at least changes character, at this horizon, but there is no reason to think so. The horizon is defined by our particular location and the particular moment at which we observe. An observer in a distant galaxy, near the edge of our observable universe, would have their own horizon, centered on themselves, extending as far around them as light has traveled in their sky. Their observable universe would include regions we cannot see, regions beyond our horizon, and would exclude regions we can see that lie beyond theirs. The horizon is not a feature of the universe, but a feature of the observer's vantage point within it. Every observer sits at the center of their own observable sphere, and these spheres overlap and extend in all directions, suggesting a universe far larger than any single horizon contains. How much larger? This is where the question becomes profound. If the universe is finite, but simply larger than our horizon, then there is more out there, but a definite amount. If the universe is infinite, extending without end in all directions, then our observable sphere is an infinitesimal speck within a boundless expanse, and the implications become extraordinary. The evidence we have, particularly the measured flatness of space we discussed earlier, is consistent with a universe that is infinite, or at the very least vastly larger than the part we can see. We cannot prove it is infinite, because we cannot see beyond our horizon to check. But the flatness, taken at face value and extended beyond what we observe, points toward a universe that may have no edge and no end, continuing on far past the boundary of our sight. Consider what an infinite universe would mean, governed everywhere by the same physical laws as our own region. Space would be filled, endlessly, with matter arranged into galaxies, stars, and planets, following the same rules of physics that operate here. There would be no special place, no center, no edge. Wherever you went, you would find more of the same kind of universe, more galaxies stretching to each new horizon, without limit. Our observable universe, vast as it seems to us, containing hundreds of billions of galaxies, would be one tiny region among infinitely many such regions, each beyond the horizon of the others, each a complete observable universe to its own inhabitants, if it had any. The cosmos would be not a single observable universe, but an unbounded sea of them, all sharing the same laws, all formed from the same kind of matter, differing only in the particular arrangements of their contents. This brings us to a route to parallel universes, quite different from the quantum branches and from the inflationary pockets, and in some ways the simplest of all. These other regions beyond our horizon are not exotic. They obey the same laws as ours. They are made of the same particles, governed by the same forces, formed by the same processes. They differ from our region only in the specific arrangement of matter within them, in which galaxies formed where, in which stars burn in which patterns. They are parallel universes in the modest sense of being other regions of the same vast space, separated from us not by any deep barrier, but simply by distance too great for light to cross in the available time. Of all the parallel universe ideas, this one requires the least. It requires only that space be large enough, perhaps infinite, a possibility the evidence permits and even gently favors. Yet from this modest beginning, an extraordinary conclusion follows, one that we will develop fully in what comes next, but which we can begin to glimpse here. If space is truly infinite, filled endlessly with matter arranged by the same physical processes, then the number of regions like our own observable universe is also infinite. And within each region, matter can be arranged in only a finite number of distinct ways, because the amount of matter in a region is finite, and the ways of arranging it, while staggeringly numerous, are not without limit. A finite number of possible arrangements, distributed across an infinite number of regions, leads to a startling result. Some arrangements must repeat. With infinitely many regions, and only finitely many ways to fill them, the same arrangements must occur again and again, somewhere out there in the boundless expanse. The cosmic horizon, then, is not merely a limit on our vision. It is the boundary that separates our particular arrangement of matter from all the other arrangements that the rest of an infinite universe might contain. It hides from us not just distant galaxies, but the full variety of what an endless cosmos holds, including, if the reasoning holds, regions that duplicate our own. We sit at the center of our observable sphere, able to see only this one arrangement of matter, this one particular history of galaxies and stars, while beyond the horizon, forever hidden, lie countless other arrangements, some utterly different, and some, the mathematics insists, identical to ours in every detail. The horizon is the edge of our knowledge, but not the edge of reality, and what lies beyond it may include things far stranger than mere distant galaxies. There is a precise way to state how far one might have to travel in such an infinite universe to encounter a region identical to our own, and the reasoning behind it is rigorous, even though the distances defy imagination. The key is that the contents of any region, the size of our observable universe, can be specified completely by listing the state of every particle within it. And although this is an enormous quantity of information, it is finite. A finite specification means a finite number of possible distinct regions. However large that number is, in an infinite universe with infinitely many regions, every possible specification must be realized, not once, but infinitely often. Somewhere at some vast distance, there is a region whose every particle matches ours, a region indistinguishable from the one we inhabit. And between here and there lie all the other possibilities, every arrangement that differs from ours by a little or by a lot. This is a conclusion that follows from simple assumptions. An infinite universe, and the same physical laws everywhere. Yet it leads somewhere that challenges our deepest sense of who and what we are. For if every possible arrangement of matter is realized somewhere in an infinite cosmos, then among those arrangements are some that match not just our region in general, but ourselves in particular, down to the last detail. The implications of this reach beyond astronomy and physics into the question of identity itself, into what it means to be a unique individual in a universe that may contain, somewhere beyond the horizon, exact copies of you. To understand how this can be and what it would mean, we must follow the reasoning carefully into the question of duplication, of distant twins, and of just how literally the universe may repeat itself. The claim that an infinite universe must contain copies of you sounds like a leap into fantasy, but it rests on reasoning as solid as basic arithmetic. To see why, we need to think carefully about what it would take to make a copy of a region of space. How many distinct regions are possible, and what happens when a finite number of possibilities is spread across an infinite expanse? The conclusion that follows is strange, but each step that leads to it is difficult to deny, and that combination of strange destination and solid path is exactly what makes the idea worth examining closely rather than dismissing. Begin with the question of what defines a region of space, like our observable universe. Such a region contains a certain amount of matter, arranged in a certain way. To specify it completely, you would need to describe the state of everything within it, the position and motion of every particle, the configuration of every atom, the pattern of every field. This is an enormous quantity of information, almost beyond imagining in its scale. But here is the crucial point. It is finite. The region has a finite size and contains a finite amount of matter, and describing it requires a finite, though colossal, amount of information. There is no infinity hiding in the description of a single region. Vast as it is, it could in principle be written down completely, every detail accounted for, with nothing left over. Now consider that this information cannot take just any value with infinite precision, because of the quantum nature of reality we examined earlier. At the smallest scales, properties come in discrete units rather than smoothly varying values. Energy comes in packets, as we saw, and other properties are similarly grainy. This graininess means that the state of a region cannot be specified to unlimited precision. There is a smallest meaningful distinction, a finest grain below which differences cease to exist. As a result, the number of genuinely distinct ways a region of space can be arranged is not merely finite, but countable in principle. An immense number, to be sure, but a definite one. There are only so many distinct configurations that a region of our size can take, only so many ways to arrange its matter that differ in any meaningful way. This is the foundation of the entire argument, so it bears restating plainly. A region the size of our observable universe can exist in only a finite number of distinct states. The number is staggeringly large, far beyond any quantity that arises in ordinary experience, but it is finite. There is a definite count of how many different observable universes are possible, how many different arrangements of matter a region of this size can hold. No arrangement can be infinitely detailed, because the graininess of reality forbids it. So the catalogue of possible regions, however enormous, has a definite length. It does not go on forever. It contains a fixed number of entries, each one a possible way for a region of our size to be. Now bring in the infinity of space. If the universe is infinite, as the flatness of space permits and gently suggests, then it contains an infinite number of regions, the size of our observable universe. Space stretches without end, filled everywhere with matter arranged by the same physical processes. And within this endless expanse, there is room for infinitely many regions like ours, each centered on its own location, each containing its own arrangement of matter. We have, then, a finite catalogue of possible arrangements, and an infinite number of regions to be filled from that catalogue. The consequence is immediate and unavoidable. If you have only a finite number of possible arrangements and an infinite number of regions, then every arrangement must occur, and must occur infinitely often, because there is no way to fill infinitely many regions while using each arrangement only a finite number of times. The logic here is the same as a simple counting principle. If you have more objects than categories, some category must contain more than one object. Stretch this to infinity, and the conclusion sharpens. With infinitely many regions, and only finitely many possible arrangements, not only must some arrangements repeat, but every arrangement must repeat without limit. Each possible configuration of a region appears not once, not 1,000 times, but infinitely many times, scattered throughout the endless expanse. There is no arrangement that occurs only once, because a single occurrence cannot account for its share of an infinite number of regions. Every possibility is realized over and over, endlessly, somewhere in the boundless cosmos. Among the possible arrangements is the exact arrangement of our own region, our observable universe, with every galaxy, every star, every planet, every particle in its precise place. This arrangement is one entry in the finite catalogue, one of the possible ways a region can be. And since every entry in the catalogue is realized infinitely often, our arrangement, too, must be realized infinitely often. Somewhere out there, beyond our horizon, at some vast distance, is a region identical to ours in every respect, containing a galaxy identical to ours, a star identical to our sun, a planet identical to our Earth. And on that planet, arranged identically down to the last particle, would be a copy of you, reading a copy of these words, thinking the same thoughts, living the same life. Not similar, identical, because the region matches ours exactly, and you are part of what fills our region. This conclusion deserves to be sat with, because it is genuinely difficult to absorb. It is not the claim that someone somewhere is similar to you, which would be unremarkable. It is the claim that someone somewhere is identical to you, atom for atom, with the same memories, the same body, the same moment of experience, because the entire region containing them matches the entire region containing you. And it is not the claim that this happens once. It happens infinitely often. There are infinitely many exact copies of you, scattered through an infinite universe, each in a region identical to this one. The reasoning that leads here is simple, almost elementary, yet it arrives at a picture of reality that overturns the most basic assumption we make about ourselves, the assumption that we are unique. We can even estimate, in a rough way, how far one would have to travel to reach the nearest identical copy, though the distance is so vast that the estimate serves more to stun than to inform. Because the number of possible arrangements, while finite, is so enormous, the nearest region identical to ours would lie at a distance so great that expressing it requires numbers far beyond those used to describe the observable universe. The point is not the specific figure, but the principle. The copies exist, infinitely many of them, but they are separated from us by distances so immense that the universe within our horizon is, by comparison, vanishingly small. We will never reach them. We will never see them. They lie forever beyond the boundary that the speed of light and the age of the universe impose. Yet if the reasoning holds, they are out there, as real as we are. It is worth being careful about the assumptions, because the conclusion is only as strong as they are. The argument requires that space be infinite, which we cannot prove, though the evidence is consistent with it. It requires that the same physical laws hold everywhere, which is a natural assumption, but still an assumption. It requires that matter be distributed throughout this infinite space in the way our region suggests, rather than thinning out to nothing beyond some point. None of these assumptions is certain, but none is unreasonable either. They follow naturally from what we observe, and from the simplest extension of our theories beyond the horizon. If they hold, the copies follow with the force of arithmetic. The strangeness of the conclusion does not weaken the logic. It only shows how counterintuitive the consequences of simple premises can be. There is a subtler version of this idea that does not even require exact copies to be unsettling. Long before you reach a region identical to ours, you would pass through regions that are nearly identical, differing in small ways. There would be a region just like ours, except that a single distant atom sits in a slightly different place. There would be a region just like ours, except for some small difference in your own life, a choice made differently, a word spoken instead of withheld. As the differences accumulate with distance, you would pass through every possible variation of your life that the laws of physics permit, every path you might have taken, every version of events that could have unfolded. The infinite universe contains not just copies of you, but every possible variation of you, each living out a different version of a life that began identically to yours. This picture, reached through the modest assumption of an infinite universe, already strains our sense of identity and uniqueness to its limit. But it assumes throughout that the same physical laws, the same constants, the same fundamental settings hold everywhere. The copies and variations all obey identical physics, differing only in the arrangement of matter. We have not yet asked what would happen if the laws themselves could differ, if the fundamental constants that define how physics works could take different values in different places. The inflationary picture hinted at this possibility, with its pockets formed under different conditions. To pursue it, we must move from regions that differ only in their contents to universes that differ in their very rules. And to do that, we must first understand where the boundaries between such universes might lie, and how a single inflating cosmos might give rise to regions governed by entirely different physics. Return to the picture of eternal inflation, the endlessly expanding space within which pockets of ordinary universe continually form. We left that picture with a question hanging over it. The pockets are separated by inflating space, sealed off from one another by expansion too rapid for any signal to cross. But are they all alike? Do they all share the same physics, the same particles, the same forces, the same fundamental constants? Or might the process that forms each pocket set its properties differently, producing universes that differ not merely in the arrangement of their matter, but in the very laws that govern them? This question takes us deeper than anything we have considered so far, because it raises the possibility of universes that are genuinely foreign, not distant versions of our own world, but worlds built on different rules entirely. To approach this, we need to understand what determines the properties of a universe in the first place. The physics we observe, the particular forces and particles and constants that define our world, may not be fixed and inevitable. They may instead depend on the conditions that prevailed when our pocket formed, on how the inflationary energy converted into matter, on choices made in the earliest moments that could in principle have gone differently. The leading theories of fundamental physics suggest that the laws we observe are not the only possible laws, that the universe could have settled into different configurations with different properties, and that which configuration it settled into may have been a matter of circumstance rather than necessity. If that is so, then different pockets, forming under different circumstances, might settle into different configurations, each with its own physics. Consider what it means for a universe to settle into a configuration. In the earliest moments, when energies were extreme and the universe was unimaginably hot and dense, the distinctions we now take for granted may not have existed. The different forces of nature, which today behave quite differently from one another, may have been unified, indistinguishable, merged into a single kind of interaction. As the universe expanded and cooled, this unity broke apart, and the distinct forces we observe emerged, separating out as the temperature dropped. This process of separation, called symmetry breaking, is a bit like what happens when water freezes. Liquid water looks the same in every direction, with no preferred orientation. But when it freezes into ice, crystals form, and those crystals have definite orientations, definite structures that were not present in the liquid. The freezing breaks the uniformity, and the particular pattern that emerges depends on the details of how the freezing happened. The crucial feature of such processes is that the outcome is not unique. When water freezes, the crystals can form in different orientations, and which orientation appears in a given place is a matter of chance, of small fluctuations that tip the process one way or another. Different regions of freezing water develop different crystal patterns. By analogy, when the early universe cooled and its forces separated out, the particular way they separated, the particular values the constants took, may also have been a matter of chance, of small fluctuations tipping the process toward one outcome or another. Our universe settled into one configuration, with our particular forces and constants. A different pocket, cooling under slightly different conditions, might have settled into a different configuration entirely, with different forces, different particles, different constants. The laws would not be violated. The same underlying physics would apply. But its expression, the specific world that emerged, could be profoundly different. This is a genuinely different kind of parallel universe from any we have considered. The quantum branches share our physics, differing only in outcomes. The distant regions of an infinite universe share our physics, differing only in the arrangement of matter. But these inflationary pockets, if they form under different conditions, might not share our physics at all. They might have forces of different strengths, particles of different masses, constants set to different values. A universe where the force-binding atomic nuclei is stronger or weaker than ours. A universe where particles have different masses, so that the chemistry we know could never arise. A universe where the expansion proceeds at a different rate, so that matter clumps differently or not at all. These are not distant versions of our world. They are alternative worlds, built on the same foundation, but assembled into different structures. The constants of nature, those particular numbers that define the strengths of forces and the masses of particles, take center stage in this picture, so it is worth understanding what they are and why their values matter. In our physics, there are a set of fundamental numbers that are not predicted by any deeper theory, but simply measured, taken as given. The strength of gravity is one such number. The strength of the force-binding atomic nuclei is another. The masses of the various particles are others. These numbers have particular values in our universe, and as far as we can tell, nothing requires them to have exactly those values. They could, in principle, have been different. And the structure of our universe, the existence of atoms, of stars, of chemistry, of everything, depends sensitively on the particular values they happen to have. This sensitivity is the key to why different constants, would produce such different universes. The values of the constants are not arbitrary in their consequences. They determine, through long chains of physical cause and effect, what kinds of structures can form. The strength of the nuclear force determines whether atomic nuclei can hold together, and therefore whether elements beyond the simplest can exist. The strength of gravity determines whether matter can gather into stars and galaxies, and how those stars burn. The masses of particles determine which kinds of atoms are stable and what chemistry is possible. Change these numbers, and you change not just the details, but the entire character of the universe that results. A small change might make stars burn out too quickly for life to develop. A larger change might prevent atoms from forming at all. The constants are the dials that set the kind of universe you get, and turning them produces universes wildly unlike our own. In the inflationary picture, with its endless pockets forming under varied conditions, these dials might be set differently in each pocket. There would be a vast range of universes, each with its own settings, each a different turn of the dials. Most would be quite unlike ours. Many would be barren, with constants set to values that permit no complex structure, no stars, no atoms, nothing but thin gas or featureless expansion. A few, by chance, would have constants set to values that permit the rich structure we observe, the atoms and stars and chemistry that make our kind of existence possible. Our universe would be one of these few, not because anything selected it, but because among the vast range of pockets, some happen to have the right settings, and ours is one of them. The full collection of pockets would span the range of possibilities, most barren, some fertile, distributed according to the chances of how each one formed. This raises a question that has troubled physicists for a long time, a question we touched on at the very beginning and are now ready to confront directly. Why does our universe have the particular constants it has, the ones that permit complex structure and life, rather than some other values that would permit nothing? In a single universe, this looks like a remarkable coincidence, a suspicious fine-tuning of the dials to just the values that allow our existence. But in the inflationary picture, with its vast range of pockets, the coincidence dissolves. If there are countless pockets with countless different settings, then some are bound to have settings that permit life, and we, being alive, necessarily find ourselves in one of those. We could not find ourselves in a barren pocket, because barren pockets contain no observers to find anything. Our universe seems fine-tuned for us not because it was designed, but because we could only have arisen in a universe whose constants permitted us. This line of reasoning, which connects the existence of many universes to the apparent fine-tuning of our own, is one of the most discussed and most contested ideas in modern cosmology. To some, it elegantly resolves a deep puzzle, explaining the apparent coincidence of our hospitable constants without invoking design and without treating it as sheer luck. To others, it feels like an evasion, an appeal to unobservable universes to explain away a problem we ought to solve within the one universe we can see. The debate is genuine and unresolved, and it touches on the deepest questions about what counts as a scientific explanation. But before we can weigh it properly, we need to understand the fine-tuning itself in detail, to see just how precisely the constants of our universe appear to be set, and just how narrow the range of values that permits our existence truly is. Only then can we judge whether the existence of many universes is a satisfying answer or a troubling one. The phrase fine-tuning needs to be made concrete, because as an abstract idea, it is easy to wave away, and only the specifics convey its full weight. The claim is that the fundamental constants of our universe appear to be set to values that fall within remarkably narrow ranges outside of which the structures necessary for complexity, and ultimately for life, could not form. This is not a vague impression, but a conclusion drawn from detailed calculations, from working out what would happen to the universe if the constants were shifted even slightly from their observed values. When physicists perform these calculations, they find again and again that small changes produce universes utterly inhospitable to any conceivable form of complexity. The constants sit, as far as we can tell, in a small, habitable window, and the question of why they sit there is one of the genuine puzzles of physics. Consider the force that binds atomic nuclei together, the strong nuclear force. This force must be strong enough to hold protons and neutrons together against the electrical repulsion that pushes protons apart. Since like charges repel, and a nucleus packs many positive charges into a tiny space. If the strong force were slightly weaker, it could not overcome this repulsion, and complex nuclei would fly apart. Nothing beyond the simplest atoms could exist, and the rich variety of elements that chemistry depends upon would never form. If the strong force were slightly stronger, the opposite problem would arise. Reactions that depend on the delicate balance between forces would proceed differently. The processes that power stars would change, and the gradual production of elements over cosmic time would be disrupted. The force sits in a narrow band where nuclei can form and stars can function, and shifting it in either direction closes off the possibility of the chemistry we know. Consider gravity, the force that gathers matter into stars and galaxies. Gravity is, by the standards of the other forces, extraordinarily weak. This weakness might seem like a flaw, an inefficiency, but it turns out to be essential. Because gravity is weak, stars are large and burn slowly, lasting for billions of years, providing the long, stable periods of energy output that the development of complexity requires. If gravity were stronger, stars would be smaller and would burn through their fuel far more quickly, flaring and dying in a fraction of the time, leaving no long, stable epochs for slow processes to unfold. The very feebleness of gravity, which might appear to be a shortcoming, is what gives the universe the patience it needs. The long, quiet stretches during which intricate structures can slowly develop. Strengthen gravity even modestly, and the universe becomes a place of brief, violent, stellar lives, hostile to anything that requires time to emerge. Consider the balance between the matter in the universe and the rate of its expansion. In the early universe, two opposing tendencies were at work. The expansion, inherited from the inflationary beginning, pushed everything apart. Gravity, arising from all the matter, pulled everything together. The fate of the universe depended on the balance between these two. If the expansion had been too rapid relative to the gravity, matter would have been flung apart before it could gather into galaxies and stars, leaving a thin, cold, structureless expanse. If the expansion had been too slow, gravity would have overwhelmed it, pulling everything back together into a collapse before any structure had time to form, or any star had time to shine. For galaxies and stars to develop, the expansion and the gravity had to be balanced with great precision, neither too fast nor too slow, and our universe appears to have struck exactly this balance, sitting on the narrow line between dispersal and collapse. These are only a few examples, and there are others, each telling the same story. The constants that define our universe appear to be set within narrow ranges that permit the formation of complex structure. Shift them, and the universe becomes barren, either too simple, too violent, too fast, or too slow for anything intricate to arise. This is the fine-tuning, and it is a real feature of our physics, confirmed by detailed calculation, not a matter of interpretation or opinion. The constants could, as far as we know, have taken other values, and most other values would have produced a lifeless universe. That ours took the particular values that permit life is the fact that demands explanation, and the explanations on offer divide physicists deeply. One response is to say that the fine-tuning is simply a brute fact, that the constants have the values they have for no reason, and that we should not read any significance into it. The universe is the way it is. This view holds, and asking why the constants permit life is asking a question that has no answer beyond the values themselves. This response has the virtue of restraint, of not reaching beyond what we can observe. But it leaves the coincidence unexplained, and many physicists find it unsatisfying because the apparent precision seems to cry out for some reason, some account of why the dials landed where they did, rather than somewhere lifeless. To shrug at so striking a pattern feels, to these physicists, like a failure to take a real puzzle seriously. A second response invokes design, suggesting that the constants were deliberately set to permit life by some purposeful agency. This response lies outside the scope of physics, which deals with natural mechanisms rather than purposes, and we will not pursue it here, not because it is unworthy of consideration, but because it belongs to a different kind of inquiry. The point of mentioning it is only to note that it exists as one of the historical responses to fine-tuning, and that the scientific responses developed partly in dialogue with it, seeking natural explanations for a feature that might otherwise seem to require a purposeful one. The third response is the one that concerns us, the one that connects fine-tuning to parallel universes. It says that the constants appear fine-tuned because there are many universes with many different settings, and we necessarily find ourselves in one of the rare universes whose settings permit our existence. This is the reasoning we encountered at the close of the previous section, and now we can see its force more clearly. If the inflationary picture is correct, and pockets form with different constants, then the full range of settings is realized somewhere. Most pockets are barren, but a few permit complexity, and observers can only arise in those few. We find our constants fine-tuned for life, not because they were set that way on purpose, and not as a meaningless coincidence, but because we are necessarily located in one of the habitable pockets, the only kind of pocket where observers can exist to notice anything at all. This reasoning has a name, the anthropic principle, and it is widely misunderstood, so it is worth stating carefully. It does not say that the universe was made for us, nor that our existence caused the constants to take their values. It says something more modest and more logical. Among the many universes with their varied constants, observers can only arise in those whose constants permit observers. Therefore, any observer, looking at their own universe, will necessarily find constants compatible with their existence, regardless of how rare such universes are among the full range. The apparent fine-tuning is a selection effect. We are not a random sample of all universes, but a sample drawn only from the habitable ones, because only habitable ones contain anyone to draw a sample. It is the same logic by which a survey, conducted among survivors will always find that everyone surveyed survived, not because survival was guaranteed, but because the dead could not be surveyed. The power of this reasoning is that it turns the fine-tuning from a mystery into an expectation. If there are many universes, then of course we find ourselves in a habitable one, because we could find ourselves nowhere else. The apparent precision of our constants is exactly what we should expect to observe, given that we exist to observe it, provided that the full range of constants is realized across many universes. The fine-tuning, which looked like an extraordinary coincidence demanding explanation, becomes a natural consequence of the existence of many universes, combined with the simple fact that we are here. This is, to its supporters, an elegant resolution, dissolving a deep puzzle by recognizing that our vantage point is not neutral but selected. Yet the reasoning is far from universally accepted, and the objections are serious. The most pressing is that it relies on universes we cannot observe. We cannot see the other pockets, cannot measure their constants, cannot confirm that they exist, or that their settings vary as the picture requires. The explanation works only if the other universes are real, and their reality is precisely what we cannot establish. To some physicists, this makes the anthropic response unscientific, an appeal to the unobservable to explain the observable, a move that explains everything and therefore predicts nothing. To others, the response is legitimate, because the many universes are not invented to explain fine-tuning, but emerge independently from inflation and from the deeper theories of matter. On this view, the universes are predicted by physics we have reason to take seriously, and the anthropic reasoning merely draws out their consequences. The disagreement runs deep, and it cannot be settled by argument alone. It requires knowing whether the other universes and the varied constants they would carry actually exist. And that question leads us to the theory that more than any other, predicts a vast range of possible universes with a vast range of possible constants, the theory that gives the multiverse its fullest and most detailed form. The theory in question is string theory, and it represents the most ambitious attempt yet made to find the deepest layer of physical reality, the foundation beneath all the forces and particles we observe. To understand why it predicts an enormous range of possible universes, we need to understand what it proposes, how it differs from everything that came before, and why its mathematics, followed honestly, leads not to a single universe, but to an almost incomprehensibly large collection of them. String theory was not built to predict a multiverse any more than inflation was. The multiverse emerged from it unbidden, a consequence its creators did not seek, and many of them did not welcome. And that reluctant origin is part of what makes it worth taking seriously. String theory begins with a simple but radical proposal about the nature of the most fundamental constituents of matter. In the conventional picture, the basic building blocks of reality are particles, points of matter with no size, no internal structure, just locations in space carrying certain properties. String theory replaces these points with tiny strands, vibrating filaments of energy, each one far smaller than a particle, so small that at the scales we can probe, they appear to be points. The fundamental objects are not dots, but threads, and these threads vibrate, oscillating like the strings of an instrument. The proposal is that everything, every particle, every force, is at bottom one of these vibrating strands, and that the different particles we observe are not different objects, but different patterns of vibration of the same underlying kind of string. This is an elegant idea, and its elegance is part of its appeal. A single kind of string, vibrating in different ways, could in principle account for the entire variety of particles, much as a single violin string can produce many different notes depending on how it vibrates. One pattern of vibration would be an electron, another a particle of light, another a constituent of the atomic nucleus. The bewildering catalogue of particles, which in conventional physics must simply be accepted as a list of separate entities, would emerge from a single underlying object, playing different notes. And crucially, among the patterns of vibration is one that corresponds to gravity, which conventional particle physics has long struggled to incorporate. String theory promises to unify all the forces, including gravity, within a single framework, which is why it has attracted such intense effort, despite its difficulties. But the theory comes with a strange and unavoidable requirement, one that turns out to be the source of the multiverse it predicts. For the mathematics of string theory to work, for the strings to vibrate consistently and produce the particles we observe, space cannot have the 3 dimensions we are familiar with. It must have more. The theory requires additional dimensions of space beyond the 3 we move through, extra directions that must exist for the mathematics to be consistent. This sounds immediately absurd, because we plainly do not perceive any extra dimensions. We move forward and back, left and right, up and down, and that is all. There is no 4th direction of space we can point to, no extra way to move. So if the theory requires extra dimensions, where are they? The proposed answer is that the extra dimensions are curled up, compactified, made so small that we cannot perceive them or move through them. Imagine a garden hose viewed from a great distance. From far away, it looks like a one-dimensional line, a thread with length but no apparent thickness. Move closer, and you see that what looked like a line is actually a tube with a 2nd dimension wrapped around it, a direction you could walk around if you were small enough. The 2nd dimension was always there, but at a distance it was too small to notice. String theory proposes that the extra dimensions of space are like this, curled up so small that at our scale they are invisible, wrapped into tiny configurations at every point in the space we perceive. The 3 large dimensions we move through are accompanied everywhere by these tiny curled-up extra dimensions, too small to detect directly. Here is where the multiverse enters, and the connection is precise rather than vague. The way these extra dimensions are curled up is not unique. There are many possible configurations, many different shapes into which the extra dimensions can be folded, and each configuration produces a different physics in the large dimensions we observe. The shape of the curled-up dimensions determines how the strings vibrate, and how the strings vibrate determines the particles and forces and constants of the resulting universe. Fold the extra dimensions one way, and you get one set of particles, one set of forces, one set of constants. Fold them another way, and you get a different set entirely. The shape of the hidden dimensions sets the physics of the visible world, and because there are many possible shapes, there are many possible physics. The number of possible shapes is where the picture becomes staggering. When physicists worked out how many distinct ways the extra dimensions could be curled up, each producing its own consistent physics, they found not a handful, not thousands, but a number so large it defies any ordinary comparison. A catalogue of possible universes vast beyond meaningful expression. Each entry in this catalog is a different way of folding the hidden dimensions, and each yields a universe with its own particles, its own forces, its own constants. This enormous catalog of possibilities has come to be called the landscape, a vast terrain of possible universes, each corresponding to a different configuration of the hidden dimensions, each a different turn of the dials we discussed when considering fine-tuning. String theory does not predict one universe. It predicts a landscape of them, more than could ever be counted or explored. Now, combine the landscape with eternal inflation, and the two ideas reinforce each other in a way that gives the multiverse its fullest form. Eternal inflation, as we saw, produces an endless succession of pockets, each forming as inflation ends in some region. String theory provides the menu of possibilities, the landscape of different ways physics can be configured. Put them together, and you have a mechanism for realizing the landscape. Each pocket that forms in eternal inflation settles into one of the configurations from the string landscape, one of the possible foldings of the hidden dimensions, and so acquires its own physics. The endless pockets of inflation sample the vast landscape of string theory, each one a different universe with different constants. The full range of possibilities gradually realized across the endless proliferation of pockets. The two theories, developed independently for different reasons, fit together into a single picture of a multiverse populated by every kind of universe the landscape allows. This is the most complete and detailed version of the multiverse that modern physics offers, and it is also the most speculative. So honesty requires marking clearly where confidence ends. String theory, for all its mathematical richness and its promise of unifying the forces, has not been confirmed by experiment. It makes few predictions that we can currently test, because the strings and the extra dimensions lie far below the scales our instruments can probe. It remains a beautiful and powerful mathematical framework whose connection to reality is not established. The landscape, similarly, is a feature of the mathematics, a consequence of the theory's structure. But whether it corresponds to anything real depends on whether string theory itself is correct, which we do not know. The multiverse of the landscape rests on foundations far less secure than the quantum branches or the inflationary pockets, and intellectual honesty requires saying so plainly. Yet even as speculation, the landscape multiverse has a kind of explanatory appeal that keeps it at the center of discussion. It offers a natural home for the anthropic resolution of fine-tuning, providing exactly the vast range of constants that the resolution requires. It connects the strangeness of the very small, the vibrating strings and hidden dimensions, to the structure of the cosmos at the largest scales, the pockets of eternal inflation. It suggests that the particular physics of our universe, which might otherwise seem arbitrary, is one selection from a vast menu, neither inevitable nor designed, but simply the configuration our pocket happened to settle into. Whether any of this is true remains unknown, and may remain unknown for a long time. But as a vision of how reality might be structured, it is coherent, far-reaching, and grounded in serious mathematics, even if that mathematics has not yet made contact with observation. We have now traced the multiverse to its most elaborate form, built from strings and hidden dimensions and endless inflation. But there is a further idea, more radical still, that goes beyond even the landscape, beyond different constants and different foldings, to propose that every possible mathematical structure describes a universe that physically exists. This idea pushes the logic of the multiverse to its ultimate conclusion, asking whether the deepest reason for the existence of other universes might lie not in physics at all, but in mathematics itself, in the bare possibility of consistent description. It is the boldest claim in the entire subject, and to understand it we must ask what it would mean for mathematics to be not merely a description of reality, but its very substance. That final idea, that every consistent mathematical structure might describe a real universe, sits at the outermost edge of where this reasoning can travel, and it is fitting to end near that edge, because it returns us to the question we began with. We started by noticing that our best descriptions of reality keep producing universes beyond our own, uninvited, as natural consequences of equations we have every reason to trust. We have now seen this happen 4 separate times, along 4 independent paths, and the convergence is worth pausing over before we close. The first path led inward, to the behavior of particles, where the wave function explores many outcomes at once, and interference proves those outcomes are real. Followed honestly, with no collapse inserted by hand, that mathematics divides reality into branches, each carrying its own version of events, separated cleanly by decoherence, so that none can ever sense the others. The second path led outward, to the immensity of space, where a universe that is flat and possibly infinite must, by simple counting, contain regions that repeat, including regions identical to our own, copies of us scattered through an endless expanse at distances we can never cross. The third path led to the violent expansion that began the cosmos, an inflation that may never fully stop, budding off pockets without end, each a separate universe sealed behind swelling space. And the fourth led to the deepest layer of matter we can theorize, the strings and hidden dimensions whose countless foldings form a landscape of possible physics, each folding a different universe with different constants, the whole catalogue perhaps realized across the endless pockets of inflation. What is remarkable is that these 4 paths were not designed to meet. They arose from different questions, asked by different people, supported by different evidence, resting on different levels of confidence. Quantum theory, which gives the branches, is the most precisely tested theory we possess. The infinity of space rests on the measured flatness of the cosmos, strong evidence honestly extended. Inflation rests on real, but less complete confirmation, its broad outline supported, its eternal continuation a reasonable consequence rather than an observed fact. The string landscape rests on mathematics of great beauty that has not yet touched experiment at all. These are very different foundations, and it would be a mistake to treat them as equally certain. Yet from each, by careful reasoning rather than wishful thinking, the same kind of conclusion emerges. Reality may be far larger than the part we inhabit, and our universe may be one among many. This convergence is not proof. 4 uncertain arguments pointing the same direction do not add up to one certain argument, and we should resist the temptation to let their agreement persuade us beyond what each can support on its own. It is entirely possible that one or more of these paths contains a flaw we have not yet found, that the branches are an artifact of an incomplete theory, that space is finite after all, that inflation does not continue forever, that string theory does not describe our world. The history of physics is full of compelling pictures that later proved wrong, and humility requires holding even the most elegant of these ideas loosely. The multiverse, in all its forms, remains a hypothesis, or rather, a family of hypotheses, none yet confirmed, some perhaps unconfirmable. And that word, unconfirmable, points to the deepest difficulty of all, the one that hangs over everything we have discussed. The other universes, by their very nature, lie beyond observation. The quantum branches are sealed by decoherence. The distant copies lie beyond the cosmic horizon. The inflationary pockets are carried away by expansion faster than light can follow. The landscape universes, if they exist, are scattered across regions we can never reach. In every case, the same feature that makes the universes parallel also makes them invisible. We cannot travel to them, cannot signal them, cannot detect them directly. This is not a temporary limitation of our instruments, to be overcome by better technology. It appears to be a permanent feature of what these universes are. They are defined, in part, by their separation from us. This raises a genuine and unresolved question about whether such ideas belong to science at all. Science, in its usual practice, advances by testing predictions against observation, by confronting theory with evidence that could prove it wrong. A claim that cannot even in principle be tested seems to fall outside this practice, however reasonable it may be. Some physicists hold this line firmly, arguing that universes we can never observe are not proper objects of science, no matter how naturally the equations produce them. Others argue that we cannot pick and choose, that if a well-tested theory predicts unobservable consequences, those consequences inherit some of the theory's credibility, and that to accept the theory while rejecting its conclusions would be inconsistent. This disagreement is not really about the universes. It is about what science is, about where the boundaries of legitimate inquiry should be drawn. And it remains, like so much else here, unsettled. There are, it should be said, faint hopes of indirect evidence, ways the existence of other universes might leave subtle traces in our own. If another pocket universe had ever collided with ours in the distant past, the collision might have left a faint pattern in the early light of the cosmos, a circular disturbance that careful surveys of the sky might one day detect. If the quantum branches are real, certain delicate experiments might reveal effects consistent only with their existence. These possibilities are speculative, and so far have yielded nothing definite, no confirmed fingerprint of another universe. But they are not nothing. They show that the multiverse, in some of its forms, may not be entirely beyond the reach of evidence, that the boundary between the testable and the untestable may lie a little further out than it first appears. The question is genuinely open, and people are genuinely looking. What then should we make of all this, standing where we now stand? We have followed reasoning that begins in solid, tested science and leads, step by careful step, to a picture of reality almost beyond comprehension, a reality in which our universe is one among many, perhaps among infinitely many, in which there may be other versions of ourselves living other versions of our lives, in which the particular physics we observe is one selection from a vast menu of possibilities. We cannot confirm this picture. We cannot rule it out. We can only note that our best theories, followed honestly, keep producing it, and sit with the discomfort of not knowing whether to believe what our own equations seem to be telling us. Perhaps the most honest conclusion is also the most humbling. For most of human history, we placed ourselves at the center of everything, imagining our world to be the whole of creation. Each advance in understanding has pushed us further from that center, showing our planet to be one of many, our star to be one of countless billions, our galaxy to be one among a vast multitude. The multiverse, if it is real, would be the furthest step yet along this path, revealing our entire universe to be but one region in a reality of unimaginable extent. We would be smaller than we ever thought, our uniqueness dissolved, our cosmos demoted from everything to merely one thing among many. And yet there is another way to hold it, to be the kind of being that can stand within one small region of such a reality, and using only careful thought and patient observation, reason its way toward the possible existence of all the rest, to follow the equations past the horizon, past the limits of sight, toward conclusions we may never confirm, is itself a remarkable thing. Whether or not the other universes exist, the fact that we can ask the question, can trace the reasoning, can mark precisely the line between what we know and what we can only wonder at, says something about the reach of understanding that no demotion can take away. The universe, or the multiverse, has produced at least one part of itself capable of contemplating the whole. That much at least we can observe directly. The rest remains for now, beyond the horizon, waiting in the dark, neither proven nor dismissed. An open question at the very edge of what reality permits us to know.